So as some of you may have noticed, there was a change in the schedule, and I'm very thankful to Abid Ali, and he's for agreeing to talk, and so he's going to tell us about Eisenstein series and Kac-Moody groups or finite fields.
All right, thanks very much for the introduction, and I feel honored to present my work on this occasion. Sadly, I never got a chance to meet Robert Moody at Alberta. I stayed there for 6 years, but it's it's great to have some association through University of Alberta. All right, so I'm going to talk about Eisenstein series on a quotient of rank 2 Kac-Moody groups, and this is joint work with Lisa Carbone, Kyuhan Lee, Dongwin Liu, and Paul Garrett, who wrote appendix for our paper and provided his notes on meromorphic continuation. Okay, I start with motivation. So suppose little k denotes finite field of q elements, and we consider Chevalier group, projective general linear group over field of formal Lorentz series. Few talks in this conference already discussed these groups. And we take K to be the maximal compact subgroup, such as PGL2K over the ring of formal power series, and gamma be a discrete subgroup, such as projective general linear group over polynomial ring. Okay, we consider this coset space G over K with the canonical action of G on this X. The pair gamma with this X is analogous to the classical setup where modular group acts on the upper half plane, which I denote by H. This space X has a structure of a tree such that gamma acts on it without an inversion, means it doesn't invert edges in this tree. I will talk more about it and this technical stuff via pictures when my presentation proceeds. Okay, and there is a natural adjacency operator on X, which induces an operator T gamma on the quotient graph gamma sub X. Okay, now this adjacency operator was studied by Ifrat in 1991 and Nagoshi in 1999 because of different reasons. But what they found is that Eisenstein series for this pair gamma and X, those are eigenfunction for T gamma, and whose eigenvalues represent the continuous spectrum of adjacency operator T gamma. So our work in Kac-Moody setting is motivated by this construction and all this what I showed. So this is natural motivation because Kac-Moody groups they can be viewed infinite dimensional analog of Chevalier groups, and they have an abstract presentation as a set of generators satisfying certain relation. Again, I will tell more details, technical details later. So for our work, we consider Steinberg construction of Chevalier group, and this construction is done by using highest weight integrable highest weight modules. And we restrict ourselves for rank 2, and again, field is finite. This complete Kac-Moody group is actually similar to PGL2 over field of formal Lorentz series, and we have a pair of parabolic subgroup P1 and P2, which will play the role of K from classical to Kac-Moody settings. And we have 3 in Kac-Moody case as well, on which the group G acts. So I will refer to this edge, standard simplex, and its vertices are standard parabolic subgroup P1 and P2. Robert Moody, Burton Remy, he spoke yesterday on building associated with the Kac-Moody groups, and in rank 2 case over finite field, this building looks like this. Any questions so far? Okay, so we have group P1 minus, which is analogous to the group gamma. And so we use the same notation for this group. So our goal is to define Eisenstein series for this pair G gamma, and which is induced by character on set of vertices of G. Now, in the classical setting, Eisenstein series is defined by using character defined on the torus and extended it to the whole group by using Iwasawa decomposition. So, but in our case, we are defining our character in terms of trees. So we need to find a connection between Iwasawa decomposition and the tree on which G acts. All right, so our Eisenstein series is an analog of Eisenstein series, which were defined by Efrat and Nagoshi for PGL2K over like ring of polynomial, and also it's an analog of classical non-holomorphic Eisenstein series for the modular group when it acts on the highest weight on the upper half plane. So I have divided my presentation into 3 parts. In part 1, I will introduce some basic notations, and in part 2, which is more like a connection of algebraic and combinatorial structure of Kac-Moody group, and which is where this is the place where I played most role. And third part, which is analytical side of Eisenstein series, and I don't have much to do with that part, so I will discuss it at the end. So we not only define Eisenstein series, we also discuss its constant term, convergence, and meromorphic continuation. So this last part is what I will talk at the end of my presentation. Okay, so before I move to these 3 main parts, let me state some history of this work. So for infinite dimensional Kac-Moody group, Howard Garland, he started working on Eisenstein series related to defined on affine Kac-Moody group in 1999. And from 1999 to 2011, he wrote a series of papers, and it's hard for me to write all of them, but he wrote several papers. And then Lee and Lombardo in 2014, they extended some of his work, and also Liu in 2015 defined Eisenstein series on Kac-Moody group over functional field. Moreover, Garland with his collaborator Miller Patnaik, they defined Eisenstein series for affine Kac-Moody groups and showed that its entirety. Okay, beyond affine case, Carbon and her collaborator, they studied Eisenstein series for hyperbolic Kac-Moody group starting 2017, and recently there are 2 papers which Carbon wrote with Garland, Lee, Liu, and Miller, where they defined Eisenstein series for general Kac-Moody groups. In this setting, I mean rank 2 and finite field setting, our work is locally compact analog since the tree is locally finite. And because of it, we have hard measure, and it allows us to do integration and compute, like, for example, constant term of Eisenstein series. All right, so now I'm starting first of the three main parts of my presentation. So starting with, it starts with 2 by 2 generalized Cartan matrix, where diagonal entries are 2 and off diagonal entries are non-positive integers, and we have a bound on m greater than or equal to 2 because we want to work on infinite dimensional Kac-Moody groups. Now, when m is 2, we call A to be of a fine type, and if m is greater than 3, then A is hyperbolic type. So we denote by this little g Kac-Moody algebra associated with A. It can be presented by a set of generators, which consist of Chevalier generators and Cartan subalgebra, and satisfying some relation, which I'm not going to show here to save my time and some space. But I would like to talk about some combinatorial data consisting of simple roots, which we denote by pi, and set of simple co-roots pi v. And we denote by q and qv root and co-root lattices. I'm sorry, there are too many notations, but in order to provide background, I have to introduce all these notations. Okay, so we have set of roots which you denote by delta, and each root can be written as an integral linear combination of simple roots, where, like, coefficient can be positive or negative integers. We call a root positive if if coefficient are positive integer, and we call a root negative if coefficient are negative integers. We denote by W the Weyl group, and as Chernosov pointed out in his presentation, in infinite dimensional Kac-Moody, we also have imaginary roots, but I'm concentrating on real roots, which are obtained by WX on simple roots. We denote this set by delta real, delta RE. All right, and for this specific setting, we need two subsets of the Weyl group W, which we denote by A. And these are the elements which have even length, and A plus, which have like even length, but now we are only considering positive integers. Any questions so far? Okay, so Kac-Moody group, first we consider incomplete, and it has a finite presentation in terms of these generators, and these generators can be given a concrete realization using representation theory. So, and because our Chevalier, our representation is integrable, so Chevalier generators, they act locally nilpotently, so their exponentials are well-defined automorphism of highest weight representation. So we can, so these generators which have this concrete realization, they make sense. Okay. For notational simplicity, once we fix our finite field K and lambda, which is regular dominant weight, we drop them from the notation and we just denote our incomplete Kac-Moody group by G0. Questions? Okay, now we consider some particular elements and subgroups which we would need during the course of my presentation. First up, these elements are called extended wide reflections. Those are defined in terms of the generator, which I showed on my last slide. And we set W tilde I to be the valuation of these W tilde U at 1. And we denote by H alpha I U when U is U are invertible elements inside field by W tilde I U and W tilde I. Let H be Cartan subgroup, which is generated by these HI for I is equal to 1, 2, and U again invertible elements. And for real root alpha, we define we denote U alpha, the corresponding one parametric subgroup. The group G0 has a pair of unipotent subgroups, which we denote by U0 plus minus, and those correspond to the positive and real, positive and negative real roots. So these subgroups, which we denote by U plus 0 and U minus, they are analogous to the groups of upper and lower triangular matrices, respectively. Question on these notations? Okay, so, but for our work, we consider complete Kac-Moody groups. And we consider this completion, which was obtained by Carbone and Galan in 2003 by using highest weight representation. And in this complete, we are particularly interested completion inside positive direction, means we consider completion of U plus, okay? And we denote B plus minus the direct product of H and unipotent subgroup. And we have twin BN pairs, which like Bertrand Remy referred in his last talk. And this twin BN pair structure yields not only Brouillard decomposition, but it also allow us to associate these groups with nice geometry, okay, which I will show in next few slides. And we define standard parabolic subgroup. There are two pairs of standard parabolic subgroup, which are obtained by the union of these Brouillard cells. And we have three. In rank 2 case, over finite field, the associated Brouillard text building is a homogeneous bipartite tree of degree Q plus 1, means it's locally finite. For every fixed vertex, we have Q edges emanating from this vertex. Now, we choose labeling of vertices of this building, which are like coset space of standard parabolic subgroup P1 and P2 and G. And edges are indexed by the cosets of B and G, and we put, in order to maintain orientation or specify orientation, we put this line over G over B. So we have T associated with G. So for a fixed vertex, we have like Q plus 1 edges emanating from it. And we pick this specific labeling because it's crucial for our work to define Eisenstein series and to prove its properties, such as compute its constant term and meromorphic continuation. Questions? Yeah. Positive side, yeah. Because, yeah. Okay, now I'm calling it an Iwasawa decomposition, and this is a kind of abuse of this notation. It was pointed out Siddhartha when I was giving same presentation at Rutgers in our seminar. He He advised me to use some other name for this decomposition, but because our strategy is similar, so right now I'm keeping this same notation, but it's an analog of Iwasawa decomposition, and it only occurs in rank 2 case. So let me, because this Iwasawa decomposition is important and it's crucial in defining Eisenstein series, so let me state what it is. So in rank 2 case, real roots, they distribute along branches. So we can divide, we can decompose set of real roots into 2 branches, which we denote by delta 1 and delta 2. And these 2 branches allow us to introduce 2 subgroup, curly UI, and these are the closure of the group generated by U alpha when alpha is one of these 2 branches. Okay. Carbone and Garland in the same paper in 2003, they showed that G admits this analog of Iwasawa decomposition. Okay, and A's, which already introduced, these are the these are the sets consisting of even length of the Weyl group, elements of even length. Okay, so now in classical, for classical Eisenstein series, Iwasawa decomposition only has one fixed maximal compact subgroup. But for our construction, because we want to define Eisenstein series using building or tree, so we consider G to be union of cosets coming from both parabolic subgroups, and we write it G is equal to I1 union I2, where I1 are the cosets corresponding to parabolic subgroup P1, and I2 are cosets corresponding to parabolic subgroup P2. Questions? Okay. So our first task was to find a relation between our labeling of building and this Iwasawa decomposition, and we obtained we got this task by proving this proposition, which states that every vertex on tree or building it's in bijective correspondence with I would call like Iwasawa cells of G. We require this because, as I stated earlier, in classical case, character is defined on torus and it's lifted to the whole group. And here we are defining our character in terms of tree, so we need this one-one correspondence. Okay, now here's when I'm talking about an interplay between combinatorics and algebra. So our second task was to find this relation of adjacency, which I'm going to precisely define, and relation of adjacency of vertices with the Iwasawa cells, because for every vertex we have Iwasawa cells, and for 2 adjacent vertices we need to see how corresponding Iwasawa cells are related. So that's what I'm going to do on this slide. Okay, so for fixed vertex, the set of edges emanating from that fixed vertex, we can divide it into 2 sets. We observed that these 2 sets, they are translate of vertices of the standard simplex, means they are translates of the standard parabolic subgroup P1 and P2, and it can be seen in this local picture. Okay, so for fixed vertex, which is translate of fixed parabolic subgroup, we can divide our vertices into 2 sets. One set which I denote by lambda BQ, and those are colored in blue, and this is one vertex corresponding to the other side. Okay, and these 2 sets, they correspond to 2 different Iwasawa cells. Okay, question? Okay, now because we have 1-1 correspondence, so if we denote this Iwasawa cell corresponding to V, now what we are interested in the length, okay? Because our character is defined in terms of A, elements of A, and A are even length elements of the Weyl group, and this length, this exponent Ni is playing role in our definition of character. So this is what I'm going to talk next. Okay, so, and if we, since we have correspondence of vertices with Iwasawa cells, so, and we can talk about length. So if we denote by L1i and Lmqi, the length of torus part of Iwasawa cell, then our proposition is that this length L1 of I is n minus 1 if our index of maximal parabolic subgroup, or Pj, is 3 minus I, okay? And this length is n if j is equal to I. So we have similar relation of, we have similar result for the length of Iwasawa cells corresponding to the other set of vertices, okay? Questions? Yeah.
What is UI and WI?
Well, I'm calling them Iwasawa cells. This is spherical, a kind of spherical Iwasawa decomposition obtained for rank 2 Kac-Moody groups in the setting of finite field. Do you want me to go back? Sure. Oh. Yeah. Yeah. So this and A is, these are the cosets coming from this decomposition. And A is a set of elements of the Weyl group of even length. So that's why we are considering rank 2 setting, because of this presence of spherical type of. Okay, now we can see, I mean, a picture is worth 10,000 words. So we can see the statement of previous proposition happening through this picture. So what's happening if this index 3 minus, oh, we have only 2. So if this is 2 and this is 1, then our exponent raised by 1, okay, for the set which we colored with blue. And if we have same index of the elements of A and the PJs, then exponent raised by n. Okay, so this is the difference. Okay. Now we define character. So we have enough setup to define character, and we define character by using this formula. Again, it depends on where G belongs to and which Iwasawa cell G belongs to, and we write it Q minus S 2Ni if J is equal to I, and Q raised to power minus S 2N minus I if J is equal to 3 minus I. Okay, so this is our first ingredient and the only ingredient to define Eisenstein series. Now, adjacency operator on T can be defined through this sum. So it's a sum of the value of function on the vertices which are adjacent to fixed vertex X. Okay, and we have generalization of theorems which were proved by Efrat and Nagoshi, and our character is an eigenfunction for the adjacency operator for t, and we also computed its eigenvalue, which is equal to q raised to power 1 minus s plus qs, where q is cardinality of the underlying field, finite field q. Okay. Now this will yield that our Eisenstein series, which is defined in terms of character, is also an eigenfunction for the adjacency operator. Again, another generalization for Ifrat and Nagoshi's work. Questions so far? All right, so now we define Eisenstein series. We note that gamma intersect with these spherical UIs for I is equal to 1, 2. So we define Eisenstein series on the quotient graph, okay, via this sum. And sum is taken over the set of cosets of gamma. Gamma is P1 minus. Sorry. Questions about definition? Okay. Now we talk about convergence of Eisenstein series. Our Eisenstein series converges absolutely, provided with the Goldman condition, which states that R real of S, if real of S is greater than 0 or greater than 1, then Eisenstein series converges absolutely. Okay. Now the main result which we use to obtain this convergence is this proposition, which is proven not only for P1 minus, but also it's proven for general lattice subgroup. So it states that if we have lattice subgroup and if we consider its Iwasawa decomposition, then the torus part, which are determined exponent and I gamma, they are bounded below. So that's the main part. So now when we consider Eisenstein series, so and we consider its absolute value, then this bound played the role, and we get our convergence. Okay. Question? Okay, so constant term can be computed by solving this integral. Now in rank 2 case, again we have a spherical analog of Brouillard decomposition, which is not like indexed over the elements of the Weyl group. Rather, we have only 2 cells. Okay, so this allows us to compute this integral, and this definition makes sense in our setting because, as I stated earlier, our groups are locally compact, so we can integrate with respect to Haar-Mayer. So we computed this constant term, and this is equal to linear combination of these 2 characters, okay, and C1s, sorry, I have typo here, C1s and C2s, those are constant, which depends on complex number S. Any questions so far?
Do you know what they are?
I didn't compute, but that's a good question. Yeah, we don't know.
You don't even know, for example, C1 is 51?
Yes. Now is last part of my talk, where I will talk about analytical notions of meromorphic continuation. So the series we define is meromorphically continuous, and to show this, we use Selberg-Bernstein method. Now for this one define, so all these steps, those are followed in classical setting to get meromorphic continuation. Okay, for this one defines Siegel sets and show that they have finite self-intersection. Okay, now in our case, gamma is equal to P1 minus acts on trees, and its quotient graph is just one ray. Okay, and because of this simple description, our fundamental domain is simple, so we don't need to consider Siegel sets. Okay, Siegel sets are used to approximate fundamental domain, but our fundamental domain for rank 2 setting and for this choice of P1, it's simple. So we consider fundamental domain itself, and it simplified the process of proving or getting Meromorphic continuation for our Eisenstein series. Okay, so as a result of this step, a certain truncation operator lives on a finite graph and hence is compact. In our case, this truncation operator is identically zero because of this simple description of fundamental domain. It's identically zero, so it's trivially compact. So again, our case rank 2 and over finite field made our mathematical life easier to get this Meromorphic continuation. And finally, using the compact operator criterion with Bernstein method, we obtained the required continuation. So this part, Paul Garrett wrote his notes and several years ago, but on our request, he modified those notes, and he agreed to write them as an appendix in our paper. So by using this criterion, we obtained the Meromorphic continuation of our Eisenstein series. Any question? All right, so final slide. Why our work is important? Because outside of affine case, our Eisenstein series is the first example of Kac-Moody groups over finite field. As I stated earlier, outside of affine case, Carbon with her collaborator, they defined Eisenstein series for rank 2 case over real numbers. And recently, Kyuhan Lee and Dongwen Liu and Oliver Matthew, they defined Eisenstein series over Kac-Moody groups for function field. But our Eisenstein series is the first example over finite field. Okay, in one of our previous work, we defined congruous subgroups of gamma P1 minus, and we constructed their graph of groups. Those are more complicated than P1 minus, but we proved that those are lattice subgroups. We obtained their amalgamated product. So, so one of the future direction of our work is to extend the definition of our Eisenstein series, not only for those congruous subgroups, but also other lattice subgroups, for example, B1 minus. But the problem, as I said earlier, could be, we didn't start working on it, but the graph is now, it's not like simple ray. There are few rays emanating again from one fixed vertex, so it's a bit complicated. But this is a potential direction which one can think of extending our work. All right, I think I was a little bit fast, so but I thank you for your attention.